We have seen that an EMF can be induced in a coil by keeping the coil stationary and moving a magnet nearby, or by moving the coil near a stationary magnet. Another method of changing the magnetic field in a given location in space without physically moving a permanent magnet is to change the current in a nearby coil. In this case, the field can change strength and polarity along with the current sourced by the generator. This changing field can induce a current in another circuit. Consider two coils of wire, a primary coil and a secondary coil, placed close together. The primary coil is the one connected to the AC generator, which sends an alternating current through it. The secondary coil is not attached to a generator, although a voltmeter is connected across it to register any induced EMF. The current-carrying primary coil is an electromagnet and creates a magnetic field in the surrounding region. If the two coils are close to each other, a significant fraction of this magnetic field penetrates the secondary coil and produces a magnetic flux. The flux is changing since the current in the primary coil and its associated magnetic field are changing. Because of the change in flux, an EMF is induced in the secondary coil. The effect in which a changing current in one circuit induces an EMF in another circuit is called mutual induction. According to Faraday's law of electromagnetic induction, the average EMF, ES, induced in the secondary coil is proportional to the change in flux, delta phi s, passing through it. However, this change in flux in the secondary is produced by and proportional to the change in current, delta IP, in the primary coil. It is convenient to recast Faraday's law of induction into a form that relates delta phi s to delta IP, since it is usually the current that is being controlled in the primary coil. To see how this recasting is accomplished, note that the net magnetic flux passing through the secondary coil is Ns times phi s, where Ns is the number of loops in the secondary coil, and phi s is the flux through one loop, which is assumed to be the same for all of the loops. The net flux is proportional to the magnetic field, which in turn is proportional to the current IP in the primary coil. Thus, we can write Ns times phi s is proportional to IP. This proportionality can be converted into an equation in the usual manner by introducing a proportionality constant, m, known as the mutual inductance, so that Ns phi s equals m times IP, where m is called the mutual inductance. We can solve this for the mutual inductance, giving m equals Ns phi s divided by IP. Rather, substituting this result into Faraday's law gives Es equals negative n times delta phi s divided by delta t, which equals negative delta n times phi s divided by delta t, which equals negative delta m times IP divided by delta t, which equals negative m delta IP divided by delta t. So Es equals negative m times delta IP divided by delta t, where m is the mutual inductance. The units of mutual inductance are volt times second divided by amp, which is equal to the Henry, or H. The mutual inductance depends on the geometry of the coils and on the nature of any ferromagnetic core material that is present. Although M can be calculated for some highly symmetrical arrangements, it is usually measured experimentally. In most situations, values of M are less than 1 Henry and are often on the order of millihenries or microhenries. In all examples of induced EMFs presented so far, the magnetic field has been produced by an external source, such as a permanent magnet or an electromagnet. However, the magnetic field need not arise from an external source. An EMF can be induced in a current-carrying coil by a change in the magnetic field that the current itself produces. For instance, here we show a coil connected to an AC generator. The alternating current creates an alternating magnetic field that, in turn, creates a changing flux through the coil. The change in flux induces an EMF in the coil in accord with Faraday's law. Self-induction is the effect in which a changing current in a circuit induces an EMF in the same circuit. When dealing with self-induction, as with mutual induction, it is customary to recast Faraday's law into a form in which the induced EMF is proportional to the change in current in the coil rather than to the change in flux. If phi is the magnetic flux that passes through one turn of the coil, then n times phi is the net flux through a coil of n turns. And since phi is proportional to the magnetic field, and the magnetic field is proportional to the current I, it follows that n times phi is proportional to I. By inserting a constant L, called the self-inductance, or simply the inductance, of the coil, we can convert this proportionality into the equation n-phi equals L times I, where the inductance L is again in henries. We can solve this for L to give L equals n times phi divided by I. Rather, as we had done with mutual inductance, we plug this into Faraday's law of induction to give E equals negative n times delta phi divided by delta t, which equals negative delta n phi divided by delta t, which equals negative delta Li divided by delta t. Or the EMF due to self-induction is negative L times delta I divided by delta t, where the units of self-inductance, or just inductance, L, is the Henry. Finally, an inductor, like a capacitor, can store energy. This stored energy arises because the generator does work to establish a current in an inductor. Knowing the current I and the inductance L, the energy stored in an inductor is given by energy equals 1/2 L times I squared. It is also possible to regard the energy in an inductor as being stored in its magnetic field. The energy per unit volume, or energy density, stored in an inductor's magnetic field is given by energy density equals 1 divided by 2 mu 0 times b squared, where mu naught is the permeability of free space, a constant. In summary, mutual induction is an effect in which a changing current in one circuit induces an EMF in another circuit. The induced EMF is given by ES equals negative m times delta IP divided by delta t, where m is the mutual inductance. Next, self-induction is an effect in which a changing current in a circuit induces an EMF in the same circuit. The induced EMF is given by E equals negative L times delta I divided by delta t, where L is the inductance. The self-inductance is usually referred to as just inductance. Finally, an inductor, like a capacitor, can store energy. Knowing the current I and the inductance L, the energy stored in an inductor is given by 1/2 Li squared. It is also possible to regard the energy in an inductor as being stored in its magnetic field. The energy density, or energy per unit volume, stored in an inductor's magnetic field is given by 1 divided by 2 mu 0 times b squared, where mu 0 is the permeability of free space, a constant.